Hello everyone, welcome to Engineers Ireland. You'll be glad to know that this is going to be a short talk, not like some of the more marathon ones that we had earlier. Like the last one, you will notice that there is a change now, and the change is there's a small number of sections where the ideas are very new. You certainly weren't playing around with them for junior cert. Part of the problem I think that people have with these sections when they're dealing with the Leaving Cert is that they fall into the trap of sticking with the familiar, dealing with algebra and geometry, those type of things, or something new that they really like, such as calculus. The familiar isn't necessarily the easiest, and the unfamiliar is rarely difficult. So our job is to turn something that's unfamiliar to us into something that we can work with. Now, we looked at difference equations the last day. What I'd like if we could go through now is induction. Induction is an extremely powerful tool in mathematics. Quite a number of things are proved using it, and some things proved using it couldn't be proved any other way. The idea is, it's a trick. It's probably the best way of putting it. If you have a long sequence of things and you want to prove something about them, what you do with induction is you find the smallest case where the thing is true. Now, we have a habit of calling it the first example S. Now, S clearly is the first letter of, we'll say, small, or whatever you want to help you remember this, but it's tradition to call it S. So the first one is S. And then the next step is we assume it's true for some other one that's bigger, which we will call the K case. That's just an assumption. We aren't saying it's true. We're saying we'll assume it to be true. And then what we do is we move on to the next one up from it, the K plus 1 case, and we see if we can move the expression, or the style of the expression, shape it in a form that will be dependent on the K case. And you'd say it's definitely going to be true if the K case was true. And this is where the induction comes in. We can word it this way. You can say if the K plus 1 case is true, if the K case is true. But it is true for this little case, the S case, the first case. Therefore, it's true for all cases. It might sound like a weird way of doing some maths. It's very powerful. It's also quite straightforward once you get used to it. One of the reasons why people have some difficulty with this is they're not familiar enough with the things that are being used, such as factorial. So anyway, let's start with this. Now what we'll say is if we have a statement and we can say something about this statement, and now n is just going to be some number. It could be 1, 2, 3, 4, 5, 6, all the way up along, and we're saying for all n greater than or equal to some start number, S being the first for start or small or whatever you like to call it, okay, where S and n are elements of n0. Now it can be n0 or n1 depending on how you number things. I've brought this in here just so that you can be clear on one thing. This is natural numbers, okay? It's like 1, 2, 3 all the way across. And because the Greeks didn't have 0, and really no one had them until the Indians discovered it, we also have a special case which is n0, and that is all of the other ones, but it includes 0. Now, I don't care how you actually number these things. All that matters is that once you've numbered it, you remain consistent. Traditionally, or most of the time, people just start with n equal to 1. So then, now that we have played with these little things, we're saying, what are we going to do? First thing, we'll prove the first case is true. That's simply a matter of putting in whatever the value of s is. It's often 1, but it might be as big as 5 or 7. And then you'd say, yes, okay, I found it to be true. And you found it to be true by actually working it out. Okay. The second thing is you're now going to assume that this particular case is true. We'll just assume it's true when n is k. Taking that assumption and working with it, we now look at this case. The next one, bigger. And we'll see if we can prove that that's true in a proof that's dependent on the k case being true. In other words, if only we were certain k was true, definitely this will be true. That's the kind of thing we want to get to. And once we've done that we found this is true if, and that's the big if the pk case is true. Once we get to this, once we can show this in mathematics, that the k plus 1 case will be true if the k case is true, then we can go to our third step. And you can basically state for all values of n greater than or equal to the s value that it's true. Why can you say that? If I said to you that the 8th case is true if the 7th case is true, and we already know that the first case was true, well then I would say to you, is the 7th case true? Well, it is if the 6th case is true. Is that true? Well, it is if the 5th case is true, and back to the very first one, to the s case. So we're saying, aha, it's true all the way from 7 down. Now, I just started with 7. I could have started with 1 billion. And all of them are true all the way down to the first case. And that's true for any number I'd start with right all the way up to infinity. So we're saying, assume the k case, prove the k plus 1 case, and it'll have the one condition on it, aha. If the k case is true, the k plus 1 case is true, and now we can prove back to the start case. The issue is the k plus 1 is true if the k is true, but we know the s case is true, therefore all cases are true. That's the game. The game is actually easy. You just have to be careful in how you manipulate your numbers. Now, there are 3 main types that you have for the Leaving Cert, and we'll start obviously with the easiest one. Now, just to make life handy for us all, I'll pick the examples that are given in Aidan Roundtree's book. This basically starts on page 187. So his first example is you want to prove something by induction. What he wants to prove is that 1 by 2 plus 2 by 3 plus. Now what we have to ask ourselves is, how do we get a general example? It's going to be an infinite number of these little terms going all the way across, and you'll have a number and a number bigger than it multiplied by it. So let's just think, this is the first example. This is the second one, and on and on and on. We were saying, what is the u in 1? Well, you'll notice I have 1 here, and 2 is 1 bigger than it. I have this one, and 3 is 1 bigger than it. So we can then state that the general one is n by n plus 1. Okay? Now, here's what we have to prove, is that that is equal to 1 over 3 multiplying into n outside of n plus 1 by n plus 2. You have to admit it is much easier to use this right hand side here. If I said to you I want the first million terms of this thing here on the left, well, multiplying all numbers like 1 by 2 and 2 by 3 for a million of them would be a bit of a serious exercise. It would be a lot easier to go, well, it's 1/3 multiplied by a million outside of a million in 1 and multiplied by a million in 2. So there's a lot to gain in being able to prove this. The idea is if you prove it, you can make your life easy. I'm all in favour of that. So, what are we going to say? We'll start with the first case. Now, you'll obviously look at, okay, try s equal to 1. And we'll go, first case, what do we have? 1 by 2. There's only that one. And they cancel. So you're saying true. So we're happy. We have the first case. Now, just to save space, I'll clear that off now. And we'll say, what's the second step? P of k step. And we'll say, we assume P of k is true. Now what does that mean? It means that 1 by 2 plus 2 by 3 plus all the way across until I get up to the number k that I wanted, and that is 1/3 of k outside of k plus 1 by k plus 2. We've assumed this. Okay, and now we're going to use that as a piece of information to help us. Let's look at say, what is that? Well, it's 1 by 2 plus 2 by 3 plus, and I'll write in what I have already up here. It's obviously all of these ones, plus there's one more term in it. That's the left hand side. What's very interesting here is you'll notice that we have all of these guys, all the same guys that we had there. Okay? And we have one extra guy. So what can we say? We can say that this side here, all of this stuff, we can say that we know that sum. We know how much it sums up to. And we can say it because we've assumed that it's this much. So I can replace that. So I have that much, and I also have the extra term. Now then, what can we see now? If you notice, those two terms are also here. Now I can say to you, I can name those anything. I can call them an apple for all I care. Let's just say we're just seeing this as something. And we'll say I have 1/3 k of these things, and I also have one of them. So let's go over here, and we'll say 1/3 k plus 1. So if I said I had 1/3 k apples and another apple, I have 1/3 k plus 1 apples. So 1/3 k plus 1. What is that? Does that seem sensible? Now, are you happy with that? The whole thing about these guys is that you have to recognize that once you get down at this little stage in these things, you just have to get careful. Okay? So now, if we get careful here and we're saying, I have done this. Now you'll notice I actually brought it over here. I'm doing my little bit of thinking separate from the rest of the problem. So now I'm saying, if I have the 1/3 k apples and an apple, which is 1/3 k plus 1 apples, it's exactly the same as saying that I have when I add both terms together. That's the same as I have up here, and I've just split up the 1/3 and the k plus 3. So, doesn't that look interesting? Because what we have now is we have what the right hand side would be. Which is using this top equation here, okay? The left is equal to the right. So we can say the k plus 1 case is true if the k case is true. And why we have to say if is we substitute it in. For all of this stuff here, we substitute it in that thing. Okay, so then p of k plus 1 is true if p of k is true. But p of s, which is in this case p of 1, is true. So all are true. We know the first one is true, we proved it. We know that any case is true, the one ahead of it was true, therefore we've proved them all. Now this is a nice simple example. All the concepts are in here. The only time you really have to watch yourself, because this is a game that is like a recipe. You've basically 3 steps. Find the smallest one for what it's true, and you'll call it S. Assume it true for the k, and then write the k plus 1 case. Play around with it so that you can substitute it in from the k case. Show that it's now true, but it's true dependent on our assumption that the k case was true, and then you can say it's true for the k plus 1 if it's true for the k, but it's true for the first, the S case, therefore it's true for them all. A game. Your only thing is that you have to watch for is this middle bit. this playing around and manipulating a little bit in the middle. There isn't a lot in there, which means you can take your time over this. Okay. Now then, one of the places where this is really useful is proving that a term is divisible by some number. Could be 7, 13, 129, or whatever it is. Say that we want to prove that all terms are divisible by a particular number. Okay, so these are divisibility proofs, and they're almost the same as the last one. Okay, so then, if we just, and we will spend a bit more time on this because it's the next step up. Okay, and what we want to do is start with the easy ones so as you get the concept, and then we move forward. Okay, step 1, as before, identify the S. Okay, that's the smallest. For which it is true. Two. And we play on. Now then, we have to rearrange things a little bit. In the case that's been given here, in the example, he's saying, if we're asked to prove that something is divisible by 8, and that means evenly divisible. Let's just think for the moment if we were talking about 24. Is it divisible by 8? And you say yes, 3 times. So what we could now say is that 24 is 8 by 3. If I'm thinking of a different number, we'll just say R. If we say that R is evenly divisible by 8, then we can say that R is 8 by some other number A. So can't we say if R is divisible? So if R is divisible by 8, I can write R as 8 times some other number. And that's the only little trick that you need to do in order to keep the things fairly clear on this. So let's look at one example on this. We want to prove that for any n value above some smallest value, the s value, that the answer from this is divisible by 3. We're just saying, well, if it is true, then the pk case must be 3 times some number, which we'll just call A. Okay? We assume that. And now what we can say is that implies Let's look at the pk plus 1 case. Now, if you remember, in the very first class I was mentioning to you 2 to the 7 minus 2 to the 6. I keep coming back to this because it's the basic example that you should always play with, something like this, so that you're clear when you're playing with other things that are a little more complicated over here. To solve this problem, we have to recognize that 2 to the 7 is actually 2 multiplied by 2 to the 6 minus 2 to the 6, and we're saying, isn't that now the same as that? We're trying to play the same game over here. We want to get this to look like that. Now, it's 5 multiplied by 5 to the k, okay? Minus 2 by 2 to the k. That's doing the same thing with the 2 one. Now that's very nice, because the good news is I already have a value for this. If the k case is true, I can now substitute for this one. Okay? And we're saying, what's that equal to? Now I'm going to write across the line only because I'm trying to save space here. Is that true? When you're playing with these little numbers, you do need to be extremely careful with your little signs. Okay? So I want you guys to have a careful look at this and see if the signs are alright. Because it's at these level of signs that you run into problems in the Leaving Cert. You can have all your concepts right. You can even know how to play around with your indices. But you need to ask yourself, what I'm doing now, just by way of signs, and you always, they're the things that really do kill people. Is it or isn't it true? What's just been written there. Now the interesting thing is, when you're rushing, what will happen is, what can happen is your mind can see this. Oh, 2 to the power of k. Oh, and I'm taking away 2 of them. And you'll say, oh, that means I have minus 2 to the power of k. But don't forget, it's always worth your while to have done your multiplying out. So what we had was 5 of these 2 to the k's, and I'm taking away 2 of them, so I finish up with 3 of them. Take your time at little steps like this, because you could very easily write in something that would be a disaster to you, such as minus 2 to the k. If you were multiplying, for example, 2 numbers together, and we will just say it's plus 7x, and you're multiplying it by minus 3y. Don't take it all in a big lump. Start always with the signs. Plus by minus is minus. 7 by 3 is 21, so I have minus 21, and x by y is xy. Again, in this thing, just be careful. Now, here's the nice thing. We have a very good situation that we've arrived at here. This is clearly a 3. So this piece back here, all of this back here, is divisible by 3. Yes, it is. Okay? I also have 15 here. That's divisible by 3. Now, I can say to you, I can put it in 2 ways. I can either just happily say that that is 5 by 3a, and I also have 3 by 2k, and say both sets are divisible by 3, right? Or I can say that it's equal to 3 times some other number b. Remember, we just called this thing up here, we just called that one a. We can give a new name now, because maths loves new names for things, especially when we make it easy. So we're saying all of this over here, because it has a 3 in it, and this has a 3 in it, means now I have 3 times some other number b. Well, we've now just proved the k plus 1 case to be 3 times b, therefore it's divisible by 3. Only if the k case is true, and the k case is true because we know the first case, the s case, is true. All cases are true. The k plus 1 is true if the k case is true, but the first case is true, therefore all are true. Just so as we are clear on this, we will deliberately go through one more example on this particular one before we move on to the next slightly different bit of this, okay? Notice in this case it said in 0. In the previous one we were talking about that for n's, where n went part of the ordinary integers. I'm just saying to you, always watch for the 0, because it means in this case, I'll just show it over here, you now have to consider this one. And if we look at it, anything to the power of 0 we know is 1, and anything multiplied by 0 gives you 0. So the answer is 16. So we're happy. Our S case is 0. Now you can obviously go along and say your S case is 1, and actually in the example S is taken as 1 as being the smallest one, but in reality here, even though it says it in the example, and that's one of the points I just wanted to mention to you, in the example they give you S is equal to 1, but we should be checking for the 0 case because it's in 0. Now the second thing that we're doing, we've just said if this thing on the left hand side, we're assuming it to be divisible by 16, well that means it must be 16 times some number, okay? Now you'll notice that we can get progressively more formal in how we do these. The first ones that I was looking at, I was deliberately being a little vague in how I was writing it because I just wanted you guys to get the concept. Now in reality, remember, in the exam you are writing a communication document. There are marks for being a good communicator. Mathematics loves you to be accurate because there's no room for vagueness in mathematics. So what we can say here is Look at, assume the PK case. That's a very clear message. We're telling exactly what we're going to do. Now we're saying to prove the PK plus 1 case. It's a clear indication of what we wish to do. It's very important to follow these. So we're talking about 5 now to the power of k plus 1 minus 4 to the power of k, or sorry, multiplied by k plus 1 plus 15. And we're saying, okay, what do we have here? We'll simplify it just anyway. 5 to the k plus 1 this is what we're dealing with now. That's just simplified down this bit here. We're saying we're now going to go on a quest to prove that that's divisible by 16. And we're going to do it by trying to twist it or change it into looking like all or part of the PK case. Okay? Now notice up here we do have a 5 to the k, and if I just move all of this stuff over to the right hand side, I have an expression for 5k. So I can do that now. Again, I'm just pushing it across to the right to save space on this screen here. So we're saying it's 5 outside of and once we simplify, and the nice news, that number, and that number are divisible by 16, so we can say, aha, that is now 16b. 16 times some number. So we can say that the pk plus 1 is true if, now in reality we should be using the double if, the IFF, and that means if and only if. So the PK plus 1 case is true if the PK is true. PK case is true. But P0 is true. And now you can say, therefore, all cases are true. Once you get in on this system, what you find is that, and by the way, how you get in on it is by doing the examples. Once you've got 3 or 4 examples together, you realize that there's a process. It's a very clear process. It's not like many questions that you can get in other sections where it would be harder to actually see your way through. In these particular things, it's so stylized, it's so formal, that the only time you have any little bit of difficulty is when you've gotten your PK plus 1 case and you just want to manipulate it or organize it to make part of it look like the PK case. And once you've got that done, then it's easy. This basically is the end of the second one of these induction problems. The third type the inequality proofs. That's a little trickier, but if you master the previous two, then all you have to do now is learn the new trick. Okay? So the best way of looking at this is through an example. And again, I'm just going to pick the example straight from the book because it's clear until we get down to a certain point, and then it'll require a little bit of talk. Okay? And hopefully you will see the extra little move that's in here. Okay? Notice it's just the n, so we don't have to check for 0, the 0 case. We're also being told that the smallest one we need to look at is n equal to 5. So our s, we would start off by looking at s equal to 5. Now, I just want to be absolutely clear that you guys know what a factorial is. So we look at them over here. 4 factorial is 4 by 3 by 2 by 1. Now again, this is the other thing you need to notice. They're common. So I can actually say that 5 factorial is 5 multiplied into 4 factorial. Or it's 5 multiplied by 4 into 3 factorial, and so on. Exactly the same as with indices, where we were saying 2 to the power of 7 is actually 2 multiplied by 2 to the power of 6. We can say that, for example, in this case, 5 factorial is 5 times 4 factorial, or it's 20 times 3 factorial. So we can always play with these. Now, in the general case then is n plus 1 factorial is n plus 1 multiplying into n factorial. Okay, let's get back to our problem. P of 5, we get 5 plus 1 factorial greater than or equal to 3 to the power of 5. Now the numbers are 720 greater than 243, and that is true. Okay, so we're happy. S is going to be the 5, so that'll be our start one. Now we've got to go to the K case. Now we're saying we'll assume this to be true. We want to prove I'm just trying to save space again. You should be writing this straight down in a line. It's just, if I clear the screen, you won't be able to see back at previous stuff. So what we're saying is we want to prove the pk plus 1 case. That's our goal, to prove this one. Now, we do a slightly different thing this time. We, in the two previous types of induction, when we went on to the pk plus 1 case, we then started to manipulate that case to give us all or part of the pk case. This time round, what we're going to do is we're going to stick with the pk case and see if I can transform it into the pk plus 1 case. And that's generally the thing that we do with these guys. So that's also why I pushed the two proof piece over here. So let's look at the pk case. Okay, what can we say about these particular things? I have that much. Now, there's one last thing that we will have to do with these other ones. We'll have to replace an expression, and you'll see that in a minute, and we're going to replace it with a one that will be quite similar, but a one that we can deal with, and the only trick in this is getting the new replacement one. Okay, so let's look at this. What do we have? Assume this guy. What is the pk plus 1 case? Well, let's look at factorial k plus 2. Isn't that equal to k plus 2 multiplying into the k plus 1 factorial? That's pretty obvious. In your mind, by the way, if ever you get into difficulties with trying to wrap your head around k plus 1 factorial, always go across to your right hand side, draw a nice vertical line, and give yourself an example. If we look at it, 5, we'll pick 5 factorial. It's 5 by 4 by 3 by 2 by 1. Isn't that the same as 5 multiplied by 4 factorial? Okay? So we can then say the k plus 1 factorial, isn't that, sorry, k plus 2 factorial, isn't that k plus 2 multiplying into the k plus 1 factorial? Like, that's like the 4 and that's like the 5. Now, that's us saying what that pk plus 1 case was. Remember I said to you, in these ones, what we want to do for these inequality proofs is we want to continue with the pk case. This here is the pk case. And what we'd love to do is to turn it into the pk plus 1 case. Now, look over here, we have this bit, which basically is that bit. So I'm saying then, for the pk, if I multiply that by, just multiplied by k plus 2, I now have k plus 2 by k plus 1 factorial, and we're saying that is greater than or equal to all I've done is I've gone to the pk one and I'm multiplying everything now by k plus 2. So we have k plus 2 by this thing. That thing is just what we have up here. And we've got k plus 2 by this thing, which is up here also. So yes, I've multiplied k plus 2 into each of the sides of the k case. Okay? And now we're saying to ourselves, this here, that's exactly what I have in the k plus 1 case. Okay? We've managed to bring the left hand side of the pk case to look like the pk plus 1 case. And we have a little problem now, because the right hand side has a k plus 2 outside of 3k. And what we would really, really love to be able to have is something that would look like 3k plus 1. Because that's what we're trying to prove. Look up at the very top line. We want to show that it's greater than or equal to 3 to the n, and when n is k plus 1, that's what we'd have. What we've got instead is some number multiplying into 3k. We don't have a 3k plus 1 or anything like it. So then, what can we do? This is the trick in this one. The tricks vary slightly in each different example, but all we need to recognize is if k equals to 1. Let's look at k equal to 1. What do we have over here? We have, it's now 1 plus 2 by 3k, which is 3 by 3k, and yes, that is 3k plus 1. So if I can have a k value of 1, I'll get the right answer over this side for myself, and I'll be able to say to us that k plus 2 factorial is going to be greater than or equal to 3 to the power of k plus 1. There's good news. The good news is the smallest value that k can have, or n can have, has been defined right up at the very top for us, 5. So if the k plus 2 factorial is bigger than, greater than or equal to 3 to the power of k plus 1, it is going to be bigger than that if k is 1 or bigger, and k must be 5 or bigger. So we've it proved. It just takes a little bit of time to understand that we have to play a little game when we get down to this level here. We just have to find a way of either changing this expression into something that looks like the right hand side I wanted, which is like a 3 to the n, or we need to find some other expression that's very similar to it and then be able to argue our case. Okay, so we can say definitely I got the right answer here, 3 to the power of k plus 1, and how I got it was if I let this k plus 2, if I let the k equal to 1 there, and our k must be bigger, so we're happy here. There are 6, in this particular book, there are 6 examples of this one. I would say to you, if you wish to master induction, and by the way, it does have this sneaking habit of turning up in other sections, if you master induction, or to master it, getting down to working out those 6 examples will bring you a very long way to doing it. And once you get it into your head what you're playing with here, it actually becomes a familiar thing rather than, oh my goodness, I haven't seen that in my previous 5 years in secondary school. This isn't hard. This is just not familiar, and it's your job to convert it from not familiar to familiar, and you do that by doing examples. This stuff here, like the recurrence relationships, which we just covered the last day also in a very slow, patient way, they're really important because they help you play around with expressions. They give you a new tool on how to prove things, and they have a terrible habit of turning up all over the place. The next day, what I'd like us to do is to deal with series and sequences. It may be just half of it. In other words, I may actually do 2 sessions on this. If we get that one next, okay, then we have, along with this induction and with the recurrence relationships, we have made the special question in part B in paper 2 much, much easier, because that section is not calculus, it's further calculus and series. This one and the recurrence relationships are the setup for series and sequences, and then we will lead straight into calculus on this stuff. Okay, goodbye for now, and I'll probably see you in a few more days.